Good morning. We are this semester's DCE 480 Design Team 6. Our project this semester is the Haptic User Interface Phase 2. I am James Hunter, and I'm a computer engineering major.
I'm Kristen Kirkhoff, I'm an electrical engineering major.
I'm Eric Bell, I'm an electrical engineering major.
I'm LaRon Wilson, I'm an electrical engineering major.
My name is Bin Tian, I'm an electrical engineer.
Our facilitator this semester is Dr. Virginia Ayers. Our sponsors, or our main sponsor for this semester is the MSU Resource Center for Persons with Disabilities, and that's headed by Mr. Stephen Blosser. Our other sponsors include Marathon Oil, Chrysler, and the MSU Artificial Language Laboratory. Today we're going to go over an introduction to haptic technology and why it is useful and important to our project this semester. We'll also talk about last semester's Phase 1 project and the results from that, which will lead into our Phase 2 specifications. We'll also talk about the proposed designs that we came up with to solve the problems from last semester, and then we'll go into more detail about the proposed design that we picked to implement. Later we'll go over the project management plan and how we split it up into 4 stages and where we're currently standing. Then we've identified some risks and potential solutions to those risks, and then at the end we'll go over preliminary budget.
So does anyone know what a haptic device is? Well, haptic technology is tactile feedback technology which takes advantage of the sense of touch by applying a force, vibration, or motion of the user. This technology increases the accessibility of graphic images as well as enhance the learning experience of its users. And it is said to be doing for the sense of touch what computer graphics does for vision. Here's some haptic devices. You can see that they can range from anywhere from being entertainment purposes, such as a Rumble Pack on an N64 controller, and as well as a touchscreen, and more imperative uses for those who are visually impaired. And you can use devices such as feeling a 3D image, and the Opticon down here in the bottom left allows for the user to sweep this camera over the black ink, and you can feel exactly a trace of what is being read by the camera. The downside to this device, though, is it's extremely outdated. It was built back in the 70s. They don't even make it since mid-90s. And also it only allows for one finger to feel the tactile rods compared to today's devices. Haptic user interface is an input-output device, meaning that a graphic image is your input from the computer and the output is a pinout display. We also have some examples of Braille that you can have graphical images printed on Braille paper. The downside to that, though, is you can have a huge stack that is very inconvenient for a student to carry around, and it's not, an immediate base need. You have to go to the Resource Center, have it printed out, wait for it. It can take a while. So there are devices that allow you to electronically feel images from the computer. The huge downside to that is they're expensive for students, ranging anywhere from $5,000 to $10,000.
This project was actually originally started in the fall 2012 semester, which we'll refer to from here on out as the Phase 1 design. And this is actually a picture of the Phase 1 design from the last semester's group. They were successful in creating a refreshable haptic user interface. Basically, quick overview on how it works. The user would place their hand on the device. You can see holes there. And what the device did is it utilized solenoids, and the force from the solenoids would actually push the tips of the pins up above the device through the holes, and it would constantly refresh, and the user could feel what the image is supposed to be. It utilized microcontrollers, custom computer software, and it actually plugged into the computer with a USB interface. It also required AC to DC and DC to DC power converters. There were some opportunities with the device, however, that were identified by the test users. One of those was that there was significant vibration from the pins, which made it very difficult to discern the image. Additionally, the pins would raise fairly far above the surface, which made it very different from Braille, which, as you can feel, is just barely up above the surface of the paper. Additionally, the resolution was fairly low. The pins were spaced far apart, and it was a very small matrix of pins. There was also heat dispersion. It would get quite warm after a time. Basically for phase 2, our primary goals would be to increase the resolution and reduce the vibration on the pins so that users can actually feel better what the image is supposed to look like. Secondary, we would like to reduce the heat on the device, possibly use smaller pins to make it more like Braille, which is what they're used to using for the most part, and reducing the height that the pin actually travels.
Okay. For our first proposed design, we decided to increase the number of solenoids and pins. This will address the resolution issue. So we decided to put solenoids in between each row to actually double the resolution, as you can see from the image. And our second proposed design was to have smaller solenoids and pins. The current device had 32 pins, 32 solenoids. So we wanted to make it a device more resolution. So we use an 8x8 matrix with 64 pins, 64 solenoids. To fit that into the device, we had to use a smaller solenoid. The diameter of it was 8 millimeters, so we want to use it to like 6 millimeters or 4 millimeters. And also the new pin size would decrease from 3/8 to 3/16 to make it to like more of a Braille dot. And also we have to do some software modification for the 64 pins as well. And also for our third proposed design is our magnetic latching. We will use the 8x8 matrix again with 64 pins, 64 solenoids. And that will also address the resolution issue. And we're actually going to use a magnetic bar with pins, and that will also give it a latch so it can just stay up and down. And also have like a pin that will shoot up and shoot down through a hole. And we have a pin that will actually send a pulse, a pulse to the bars and to both bars from a power source. And these pulses will charge up the polarity for it to move up or down, the magnets to move up or down, which will shoot the pin up or down, so it will give it that Braille texture. And basically this prototype is the design, proposed design 3. It worked pretty good, but the only bad thing about it was the alignment issues. Sometimes when the magnet shoots up, it was pretty much unstable, so we decided to go with another prototype, which Eric will tell you more about.
This is our current prototype, which performed much better than the first one overall. And basically what this consists of is we used a hypodermic needle and wrapped that in copper wire, which in turn creates a solenoid. Inside of that we have a neodymium magnet pin, as you can see on the right there. And when we send a short pulse, we're able to create polarization from the solenoid to create force to push the pin up. As you can see, it's also restricted here, so the height issue has been addressed there. Also, it's more stable. And additionally, the hypodermic needles, they're stainless steel. They come in standard bore sizes, so it's easy to get the size that we need, and they're also very inexpensive. This is just kind of a visual of how the polarity works to push the pin up and down. And what this is actually, that's the polarity on the pin, not the actual bars that you see. This is a visual just showing that the pin would raise up above the bar with this polarization, or if you reverse it, we're able to push the pin back down.
Okay. To drive the solenoid, we have to come up with a solenoid driver circuitry design. This is a solenoid circuitry design designed by the previous team. The output is a solenoid which acts as an inductor. We ran a simulation. As you can see by the signal output, the vibration issue is caused by these circuits. So therefore we have to come up with our own circuitry design. We created the push-pull circuitry, push-pull and RC circuits in order to have the shorter pathway. A shorter pathway will give the better control and eliminate the vibration issue. It also will reduce the heat dispersion. However, the problem with these circuits is our current and voltage signals do not match to each other. The second issue with this circuit is with higher inductance, the current and the voltage signals are diminishing. So we have to revise based on the previous circuitry experiments, we have to revise our circuits. So this is our revised circuits. It includes the addition. It includes the addition of the comparator and the differentiator. The input signals comes from the microcontroller, which ranges from 0 to 5 volts. From the simulation results, we can say when the input signals are rising up, the output voltage signal is a positive pulse, which is corresponding to the current in the solenoid. Therefore, the magnets in the solenoid will be forced up by the current created by the solenoid. Vice versa, when the input signal is falling down, the output voltage signal is a negative pulse. The current will change the direction, and the solenoid will switch the polarity to allow the pin to fall. Additionally, the comparator and the differentiator will solve the signal decaying signals issues.
So our project management plan was split into 4 stages. The first stage involved research into haptic technology and trying to find out exactly what it is and why we should use it. In addition to that, we needed to research last semester's project to find out exactly what worked on it, what didn't, and what we needed to improve on. Stage 2 was to figure out the solutions to those problems and then build our prototypes based on the design that we wanted to build. We're currently in stage 3, which involves the full-scale implementation of our chosen solution, and then testing on that device. And then we need to modify the software that was used from last semester to incorporate the larger matrix and basically the larger matrix. Stage 4 will be the final part, which is the overall finishing of the product and getting it ready for designers. We've identified some risks with the device, and they include the heat problem, which has been discussed earlier, the noise which comes from the metal pins clinking against the box, which could be distracting in some cases, or potential for pins to be projectiles. The solutions to these problems are to include heat sinks or small fans to get rid of the heat, and including rubber stoppers, and figuring out which type of casing material we could use to reduce the noise and ensure proper safety for the device. Our preliminary budget this semester includes the neodymium magnets, the Arduino Leonardo microcontroller, power supply, PCBs, and the casing. These are all estimated costs. A lot of the parts that we'll need are free from the ECE lab. This gives us a total of a budget around $260 which is well under what we were allowed for this semester.
So to summarize today's presentation, we began out with a brief introduction and description of haptic technology and the devices currently on the market. Then moved on to last semester, phase 1 solution, and we talked about, while it was very great, it had some drawbacks such as a low resolution and the pins were constantly vibrating. We then showed you our design requirements, which were to increase the resolution, eliminate vibration, while still maintaining an affordable device for students to use on campus. And then we showed you our design solution, including testing of prototype 1 and 2. And finally, we reviewed over our possible risks for the project and as well as a preliminary budget. To further enhance the importance of our project, we wanted to share with you an example that occurred in the last couple weeks. Jordan, who is a sophomore computer science major here at MSU, and she's blind, she's been working on testing with us. She actually had a homework assignment that she was unable to complete because this was just a JPEG. Our device will be able to solve this problem, and she'll be able to finish up. Thank you. Any questions?
Thank you. Are there questions? Go ahead.
The pin as a projectile thing sounds pretty scary. What exactly causes that, and what can you do to prevent it?
Possible pin projectile would be just from the force of that solenoid, it could shoot the pin further than would need be. Right now, the casing that it's in, it shouldn't. I guess only that would just be kind of if someone's shaking the box a bunch, under rigorous conditions that someone's putting this device through. But right now, once we get it into its final casing and that kind of stuff, we would be able to just close off. Once power that off, all the pins retract even further, so that shouldn't happen. That's just kind of a...
I know you mentioned like mechanical stops to prevent it.
Yeah,
from
rubber
going out,
stoppers
but,
as well would help. That.
I mean, is there anything electrically you can do, like watching the modulation, or if there's too high of a voltage, will it shoot out, or?
Yeah, I think we're gonna calculate like magnets blocks and current through the solenoid, try to solve the maybe at least estimate the forces gonna give to the magnets. So I think we will do some calculation to estimate that.
Okay.
Another question? I always have questions. How much less, have you estimated yet how much less your heat dissipation is, or how much power you're using?
We have not, because we just recently were able to come up with a design that we feel is going to work. So we haven't been able to do that yet.
Other questions?
Yeah, I have one question. You redid the circuit there to drive the pins,
Yeah.
and you did a simulation of that.
Yeah.
And you added an op-amp or something. Maybe you could explain that again, why that was needed?
Yeah, actually I run a simulation for our first design. And so you can see if we run a longer time, the signal gonna diminition. And I think it's because NPN transistor doesn't work very well. The signal is not like cannot get below the negative pulse. So when I designed a new circuit, I use op-amps as a comparator. I basically transfer from the 0 to 5 volts to the -5 to 5 volts. So and this is a differentiator. So it's deal with like a rising edge and a falling edge. So I can get like a pulse. When I get the pulse to, it's basically the push pulse circuit is switched. So I give the pulse to the switch and it's turned on. And this the push pulse basically is a current amplifier. So it's the voltage waveform ratio is 1:1. So we're gonna give a higher current to the solenoid. So that's why I use the op-amps to kind of convert the signal from -5 to 5.
Thank you again.
Any questions? Let's thank them again.